All right, ladies and gentlemen, so as promised, here is our lesson on double angle formulas. This really is just a continuation of our discussion during 7.2 when we were looking at our compound angle formulas. So we're going to develop new double angle formulas, and a lot of these questions will seem very similar. So what we're going to do is we're going to take our compound angle formulas as well as our Pythagorean formulas from our trig identities to see if we can figure out something like this. So if I have the sine of 2a, well, from our compound angle formulas, what we can do is we can just think about 2a is just a plus a. So if I think of this as sine a plus a, this is our double angle, or sorry, excuse me, our compound angle formula given to us by sine A cos A plus cos A sine A, where both angles, normally we would have A and B, now it's just A and A. And if you look, well, sine A cos A and cos A sine A, that's the same thing, they're just written in opposite order. So this whole thing just becomes 2 sine A cos A. And just like that, we have our double angle formula for our sine function. Let's do the same thing now for cosine. Now for cosine, we have a few more options. There's actually 3 different versions of this formula. I'll show you how we develop them. Like we did for 7.2, I'm going to show you the development of these formulas. You don't need to replicate it. It's just so you can see where these formulas are coming from. So we'll do the same thing here for cosine. Cos 2a is the same thing as just cos a plus a. So we'll use the same angle in our compound cosine formula. So this would be cos A minus sine A, or cos squared minus sine squared. So that's our cosine formula. Now, what I'm going to do now is I'm going to take this and let's tweak it a little bit because we can use different versions of this formula depending on the context of the question. So we've seen sine squared and cosine squared quite a bit. If you recall, our Pythagorean trig identity was this: sine squared plus cos squared equals 1. Now, what I can do is I can isolate for either sine squared or cos squared. So, for instance, I know sine squared would just be 1 minus cos squared, or I could say cos squared is 1 minus sine squared. And now what I can do is I can substitute those into my cosine double angle formula to get slightly different versions. So for instance, if I were to replace sine squared with 1 minus cos squared from my Pythagorean formula, I can simplify this down a little bit and I end up with 2 cos squared a minus 1. Similarly, if I replace cos squared with 1 minus sine squared, I'd have 1 minus 2 sine squared. So all of these are effectively the same formula. These are 3 different versions of our double angle formula, just rearranged a little bit and substituting using this Pythagorean identity to help us in certain cases. So 3 versions of our cosine double angle formula. Lastly, we have tangent. So we'll do the same thing using our compound angle formula where the angles are both A. So I can clean this a little bit up. At the top, we just end up with 2 tan A, and on the bottom, we'd have 1 minus tan squared A. So there's our tangent double angle formula. So let me go ahead and put them all on the same screen here. So we have our sine, our 3 versions of the cosine, and our tangent. Like our compound angle formulas, you might want to flag this particular slide or even print it out so you have access to it or easy access to it while you are working on your homework later on. Again, on the test, I will give you all of these formulas for when we're working on trig identities and when you're writing the test itself. These will be given to you. You don't need to memorize them. You don't need to derive them. As long as you know how to use them, we're good. So let's go ahead and put them into use. Let's do some examples. So let's say we have these 3 examples. So these should hopefully look familiar as different versions of our double angle formulas that were just on the screen. So for instance, for part A, 2 sine 3 pi over 8 cos 3 pi over 8. So I have the same angle twice. 2 sine cos. Well, that is just our double sine formula. So I could say, well, this is the sine of 2 times 3 pi over 8. So cleaning that up, 2 times 3 pi over 8 is 3 pi over 4. And just like that, we have one of our special angles. So now I can go ahead and throw this into our cast law using our special triangles. And I would see that sine of 3 pi over 4 is root 2 over 2. Going over to B, again, we have an ugly angle here, 67.5 degrees. I would have to use my calculator in order to solve this, but again, I'm looking for those special angles. But I have cos squared minus sine squared. Well, that's just my cosine double angle formula. So the cos of 267.5, well, that's the same thing as the cosine of 135 degrees. And 135 degrees, again, that's one of our special angles. I can go ahead and sub that into our cast law and get negative root 2 over 2. Lastly, pretty cleanly or pretty obviously, for part C, this is our tangent rule, where the A value is 5 pi over 12. So this would be the tan of 2 times 5 pi over 12, or 5 pi over 6. Again, that's a special angle. I can throw that into cast and get negative root 3 over 3. So using our double angle rules, still focusing on the special angles to get exact values. Okay, let's go over here. We've done a couple questions like this before. So this one's we're not using special angles, but I am giving you the ratio directly, meaning we should still be able to keep all of our answers exact. I don't want to pull out the calculator if I can avoid it. So I have the cosine of theta is equal to negative 2/3. So I want to know, well, what are the exact values of cos 2 theta and sine 2 theta? So like before, what I'm going to do is let's draw this out on my Cartesian plane and see what my triangles would look like. Now I'm going to have two different triangles here because two different triangles are going to exist between 0 and 2 pi when cos theta is negative 2 over 3. So the first one would be here. So we know cosine is negative in quadrant 2. So let's put in the values that they gave us. I know my hypotenuse would be 3, and my adjacent side there would be negative 2 because we're going to the left. And then using our Pythagorean theorem, I can very easily find that missing side, and it would be the square root of 5 right there. Now, notice that I can get plus or minus the square root of 5, and that is because we do have our second triangle. Cosine ratio will also be negative here in quadrant 3. So I could do the exact same triangle down below the x-axis. My x value is still negative 2, my hypotenuse is still 3, but now my y value would be negative 5. So there's my two different triangles. So if I wanted to now take those values and solve for the cos of, or let's start with the sine of 2 theta, excuse me. So sine 2 theta I know is 2 sine theta cos theta. So let's use these two triangles. Well, if I'm solving for the sine of theta, I can either get root 5 over 3 or negative root 5 over 3, depending on which triangle I use. So I'll just do them both at the same time. So I get plus or minus root 5 over 3. And the cos of theta, that's given to us as negative 2 over 3. So I can simplify this down, and I get 4 root 5 over 9. So two different answers, positive 4 root 5 over 9 and negative 4 root 5 over 9. Going after cos 2 theta, I'll use this version of my cosine double angle formula. I could use any of them. The reason I chose this one is because I'd like to avoid sine if I can. They gave me my cosine ratio, so let's just stick with what they've given us. But any three versions of the cosine double angle formula would work. So let's sub in. I know cos theta is negative 2 over 3, so cos squared theta would be negative 2 over 3 all squared. So let's expand and simplify, and the whole thing becomes negative 1 over 9. So cos 2 theta is negative 1 over 9. Let's try another example. This time I'm asking you for the tangent of theta being -3/4. So we're going to set this up in the same way, but pay attention to the angles that I'm asking for. Notice I'm only asking you for the answer between 3π/2 and 2π. So I'm only interested in quadrant 4. So let's draw this out. So for tan theta, our triangle would be here in quadrant 4. Only one triangle this time. So my x value would be 4 and my y value would be -3. And using Pythagorean theorem, I can see my hypotenuse would be 5. So there's my triangle, and now I can solve for the cosine of 2 theta. So I'll use this version of our cosine formula. Again, it really doesn't matter. I just picked this one because it's different than the last one. And I'd rather pick this one than the one that has both sine and cosine in it, because this way I only need to do one trig calculation. So the sine of theta would be -3/5. So the sine squared of theta would be -3/5 squared. Expand and simplify. And I get cos 2 theta is equal to 7/25. Okay, last example, and this is where this can become particularly powerful, is what if I wanted to sketch this? I want to know what is a sketch of -2 sine squared theta. Now, we know how to graph sine, we know how to graph tan, we know how to graph cosine, but we've never graphed sine squared. And I mean, short answer is we can't, at least not directly. That's a really weird thing to try to graph. But what we can do is we can use our trig identities, our new double angle formulas, to see if I can manipulate this so that I can get this into a form that can work. I want this to be a sinusoidal function with values of a, k, d, and c, and that I can graph. So -2 sine squared. So if we look at our double angle formulas, I want to pull something out that has -2 sine squared in it. Well, if you look at this version of our cosine double angle formula, there's -2 sine squared, just like that. So let's go ahead and isolate that. We'll move that 1 over to the left-hand side. So -2 sine squared theta is just the same thing as cos 2 theta minus 1. So while I can't graph sine squared, I can graph cos 2 theta. What I'm dealing with there, if that's my function, is I have a k value of 2 and a c value of -1. So a k value of 2 just means I'm dealing with a cosine wave where we have a horizontal compression by a factor of 1/2, and a c value of -1 just means I'm shifting the whole thing down 1 unit. So that I can graph fairly trivially. In black there, that's my parent cosine wave, and in red, that would be cos 2 theta minus 1. And if you were to go ahead and throw this into Desmos, if you were to plug in -2 sine squared theta, you would get this exact same wave, cos 2 theta minus 1 in red. So that's basically the work that we're looking at for 7.3. Like I said, a lot of the questions are going to be very similar to what we did in 7.2 and our compound angle formulas. So these are the practice questions I'd like you to try on page 407. Tomorrow, we're going to be looking at trig identities, which I know is everyone's favorite topic. So to help us out, you can see I have a link here to a worksheet. I've also posted it in our Hapara workspace. I would have that up on your screen, or at the very least, maybe print that out tomorrow, and it'll have all the trig identities that we're going to need. It will effectively act as your note for tomorrow, and all we're going to do is we're going to spend our time doing a bunch of different trig identity examples and practice those different types of questions. So that's it for today. I know you're all pretty tired after writing your test probably, but take a minute and go through these practice questions for page 407, and we will take up any questions you might have tomorrow before we start into our trig identities. Have a good night.